All right, so if this is vaguely giving you like this deep sense of anxiety, that's because it's from Orgo 1. Is everyone here from Dr. West's class? Okay, who's from Roche's class? Okay, so I said, is everyone from West's class? And you said no, and then.
Oh, you're talking about Orgo 2?
Yeah. Oh. Okay, who is in Orgo 2 with Roche? Okay, so for Dr. West, he says that you just need to very briefly, barely know these reactions. So know that hydration is H2O and H3O plus. And we're gonna cover Markovnikov and anti-Mark. Does Markovnikov mean? Oh, you had a question? Yeah. No. Yes, okay, so you're going to add your OH to the side that is most substituted. Yes, and this stuff is in the chapter 11 SI sheet. I just tested on it. It's on page 3. Thank you very much. I just really don't want to remake the chart. Syn and anti, you really don't even need to know what that means. Rearrangements. So what does it mean if we can have a rearrangement? Yeah. Yes, so if you have a carbocation and that carbocation can move around. So we cannot do that in oxymercuration, demercuration, or hydroboration. So just have this in mind. Not something that Dr. West usually tests on. He gave like one question about it once. Rush is going ham on these. So anyone in Rush's class, I don't. Oh no, okay. You have like 4 seconds. Okay. So last time we were talking about mass spec. We got through most of it. The only thing left to really talk about was this question, which is just an example. So I believe Dr. West doesn't have any mass spec examples in his practice problem sheets. So that's why I include these guys. So to recap at the end, last time, because we were kind of rushing, what does the presence of a -18 or -17 peak correlate to? Okay, and why could it be either 17 or? Yes, exactly, because the OH can either leave as an OH or it can snatch a hydrogen and take it with it. Okay, so for the second one, you guys told me that the answer is C. How did we know that that was the molecule just from the mass that was given? Exactly. So the fact that there is a odd M plus peak means that the mass of the compound is odd. So it has to have an odd number of nitrogens. Absolutely. So if wink, wink, nudge, nudge, he were to give you answer choice E that had C10, H21, 10, right? So now there's 2 options that have an odd number of nitrogens. All you do is you count up the mass of each one and you figure out which one is 101. So how you would do that is, what's the mass of carbon? 12 times 6, 72, plus 15 because mass of hydrogen is 1, plus what's the mass of nitrogen? So what does that equal? 101. Cool. You knew that because that was already the answer. You would do the same thing for the other one. Clearly, it will not add up to 101, so that one would be wrong. Great question. So if we have a nitrogen present, one nitrogen will make the mass odd. So if you have 2 nitrogens, they would balance out and be even. So odd mass equals an odd number. And it doesn't have to be 1. It can be any odd number. I'm going to do 1, but theoretically. Question? Okay, so select the most reasonable part, blah, 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 blah. Okay, if he gives you something like this, does this look like the spectrums we looked at yesterday or whatever day that was? No, but we can make it make sense, right? So which axis told us M over Z? The y-axis. X-axis, you lied. And then what axis is the intensity? The y, and what is that synonymous with? So everything is like really small numbers here. We know that intensity go up to 100, right? So this is like a ratio, pretty much, right? So a 10 intensity correlates to what? Probably the base peak, or 100% intensity, right? So we're going to say that 10 is 100%. And as you said, Anthony, as you said, that is going to correlate to the base peak. But here it tells you that this is the M plus peak. Can those be the same? Yes. So in this case, the base peak and the M plus peak are the same. And we know that the M plus peak is at 78, right? At a mass of 78. So at a mass of 79, what peak would we have? M plus 1, and then after that, M plus 2. And then he likes to give you this thing just to trick you, but that is like 0.3. That's just like a min. Right? Okay. So with this information at hand, what atoms are going to be in that molecule? Chlorine. Cool. How did we know it was chlorine besides the answer choices? 3-to-1 ratio, yes. So we could say that this is 33%, and we know that that is 1/3 of 100%, 1/3 of the base peak. So you can get rid of which answer choices? A, C, D. Cool. So now between these two, what do we have to do to find the answer? You have to add the mass, blah, blah. So 4 times 12 equals plus 9 plus, how much is chlorine? 5, yeah. Quick math. Thank you. All right, so then we have 12 times 3. Whoever you are, you lied to me. I'll never forgive you. You're going to make me do math? Yeah, it's 92. All right, so 12 times 3 plus 7 plus 35. Okay. So, which one of these is the right answer? E, and some people were like, wait a second. So how do we know E is the right answer? What does that mass have to correlate to? The M plus peak, exactly. So mass of 78 has to correspond to the M plus. Yeah, we know what you meant. Ta-da! And so now we're officially done with the chapter 9 handout. Yay! Yes. Exactly. Or it would say 10 or like 9.8. Then that would be a bromine. Yeah, exactly. Or Eric with names, but it's overwhelming. You have a question? Your name is Justin. You're Taylor. No, you're Sarah. Now we're going to do practice problems before we move on to chapter 11. So these are a pen-like problem. Know how to do these ones. Yes. These are from Dr. West's problem set, and they're also from my secret stash of questions that you're not allowed to ask questions about. So if you ever see some spicy questions you've never seen before, it's on the down low. Okay. So the question is, how many signals would you find on an NMR spectrum? Cool. So we are going to draw this out. We have a carbon, oxygen, carbon, carbon, oxygen, carbon. Cool. What's the first thing we do? Symmetry. Cool. Does this have a line of symmetry? Yes. Yes, it does. One person ruins it for everyone. I'm kidding. Yes. So we have a line of symmetry right down the middle. So that means these hydrogens are exactly the same as these hydrogens, yes. And how many other signals do we have? 2 hydrogens, but it's 1 signal. So all of those guys will be 1 signal, right? We have 2 signals. What is the integration of the blue hydrogen? 4H. What is the integration of the purple hydrogen? 6H. How many neighbors does the blue hydrogen have? None. Perfect. So it is a what? What about the purple? Also a singlet. Any questions about how I did that? Okay, cool. Now tell me, the purple hydrogens, what chemical shift range are they in, or region? 3 to 5, heteroatom region. Awesome, because the hydrogen is attached to a carbon, which is directly attached to a heteroatom. So this would be in the heteroatom region. What about the blue one? Exactly the same, heteroatom region. All right, so now that we did all that side stuff, what is the answer for this? B, because there are 2 signals. And we know that they're both singlets, and we know that they're both in the. Any questions about this one? Perfect. Okay. What's this? Did you want to take a picture of that? Yeah. Go ahead. You guys should know by now. I'm not mean. I'll do things for you if you ask. You have to ask. I mean, there are boundaries and stuff, but like, you can ask. There's probably been weirder than you. Yes. Kareem. Yeah. Go ahead. I will double check for you, but Markovnikov should be a hydrogen adds to the side with more hydrogens. Therefore, the OH would go to the more substituted side. It would be the opposite for anti-Markov. But to be completely honest, I don't remember all those rules off the top of my head. So, before we move on, I'm going to send you guys a worksheet for chapter 11, because there's a lot of like Orgo 1 review, and I'm not going to do Orgo 1 review with you because we don't have that. Or if that's, I'm going to send you just like a packet of like problems and then like explanations. That is donated by Mr. Chris. So, yay, yes. So it all depends on when Chris decides to send them to me. So hopefully tonight or tomorrow. Today's Friday. Tonight or tomorrow. For chapters 11 and 12? That too. So, Alex likes to put 11 and 12 in a blender, and they're the same thing. And then when it comes to exams, he said, no, it's only 11. And I'm like, what? I only 11. So, you have to know alcohols, and then you have to know the Grignard reaction. We're going to talk about it. Hopefully today. I really want to get to it. So we're going to skip that one for now. We're going to skip that one for now. We're going to do this one. Where'd you go? Yes. I don't have number 19. So we could do it in the exam review. Yeah, I just like screenshotted the ones I wanted and I put them in a doc. Why? Oh, okay, yeah. This one, yes, I want it. So we have 1, 2, 3 carbons. We have 1 bromine, and we have a chlorine. So how many signals do we have? Don't look. For HNMR, yes. What's the first thing we look for? Symmetry. Symmetry. Do we have symmetry? No. Okay, so what else are we going to look for? Oh, yeah. But like, okay, when you look at this, does anything pop out to you? Potential chiral center, cool. So this is a potential because it has 2 hydrogens and 2 unique groups. But there's something else that's even a little bit more obvious. There is a chiral center. Ooh. So this is a this is a chiral center. Yes. Yes, because this is just a methyl. This carbon has a chlorine attached to it. So that's why it's different. But good question. So if we have a chiral center, what is the relationship we're looking for? Diastereotopic, cool. So on this potential chiral center, these two are diastereotopic, as you guys said. So are they going to count as 1 signal or 2 separate signals? 2. So we're going to have 1 signal, 2 signals, 3 signals. 4 signals. So the answer would be 4. I'm not getting anything about NMR from Chris. The only thing that Chris is giving you guys is Orgo-1 reaction stuff. So like that little table I gave you. Yeah, for sure use those. Yeah, and that's what I always tell people. Do the SI handouts, obviously. Come to SI if you can't, but do those practice problems and do it over and over and over and over and over again until you can do them quickly. That's my biggest advice. Okay, we're going to skip those for now. We're going to do one of these. Okay. So this is one of those ones where you're going to look at the spectrum and have to figure out which molecule you're looking at. Some people were freaking out, mostly in Roche's class, though, because he didn't tell you guys that you don't have to draw molecules. And some of those practice problems on the handout, you just have to like draw it from scratch. So we're going to do the Rosemary method. Zoom in over here. And the first thing I like to do is just write down the number of signals. How many signals do we have? 3. I don't know why it's like that, but this is supposed to say bam. There are, in fact, 3 signals. What do you mean? Or this one? So this, the black, the one I highlighted, that's the integration thing. No. This is the integration. So it's just the integration signal, and it tells you that there's 2. And so this is part of the integration. Okay, so we have 3 signals. Next thing I look at is the region, because here, there's nothing on this side of the spectrum. We only have up to 3. So what region are all of these hydrogens in? The alkyl region. Okay, so that's all the information I take at first, and I look at the molecules. So what is the first thing we look at when we do NMR? Symmetry. Is there any symmetry here? There's partial symmetry. So these guys are symmetrical. So that's 1 signal, 2 signals, 3, 4. Oops, that's already too many. That can't be an answer. You could definitely. Okay, so I see what you're saying, but look, it's the triple bond, 1 carbon, 1 carbon. On 1 carbon, 1 carbon. If we had 2 methyls like that, then they would be symmetrical to one another, but they're not. Okay, so does everyone understand why I already crossed this answer choice out, or did I go too fast? Yes, because there's already 4, but there's only 3 signals. Cool. So for number 2, this has partial. Could you stop? Why are you this? So these 3 are the same. We have 1 signal here, 1 signal here. Oop, that's already 4. Cross it out. Here, we have symmetry. Yes, we have a good old line of symmetry right here. So we have 1 signal, 2 signals, 3 signals. This one could be okay. Partial symmetry again. 1. No hydrogens here because it's a triple bond. No hydrogens here because it's a triple bond. 2, 3. This could be an option. 1, 2, 3. Oh, 4. Too many. So just by number of signals, you've already narrowed it down to 2. That's awesome. Cool. So the next thing to note is that they're all in the alkyl region. Okay, these are all also in the alkyl region. So what I like to look at is integration, because we have 2, 3, and 9. So that's a big one, right? In the answer choices we have left, which of those have an integration of 9? The second one. This is the only one because it has 3, 6, 9 hydrogens that are the same. So that's our correct answer. Thank you. Like from the top? Okay, so the reason that that one is the answer is it had 3 signals, right? It was all in the alkyl region. And then on top of that, we looked at integration. So the integration was 9H, 2H, 3H. And that was the only one that had 9H because it has that little cool fish. Wait. Yeah, so 9, it just says right here, the integration is 9. I made it ugly by writing on top of it, but. Okay, so I didn't really like. So the reason I picked 9 is because like that's the most obvious one. So I started there, but you have to make sure all 3 match, right? So I went here, and 3, 6, 9. That matches. And then we need 1, 2, and 1, 3. So we have 2 and 3. Yeah. Okay, cool. Yeah, I didn't just choose one of them. We had to check all of them, but I chose the most obvious one to check first. Okay. So I'm going to let that brew for one more second while I drink my coffee. Thank you. Thank you. It's so fun. All right. We can come back to this. I really want to go to chapter 11 though. My iPad has so much. One of these days I'll show you my MCAT notes because they're beautiful. But I don't think today's the day. Stop it. Stop it, self. You know, this is what the search bar is. Okay. So everybody look away for a second while I delete this. Oh, you know what? We don't get to that anyway. Yeah, see, Grignards aren't even in this chapter. Yeah, supposedly. You know what? We're just going to do this my way. So I'm going to slightly go off the handout for a second. Everything I'm going to cover is on the handout, but it's just going to be more convenient if I just draw for you guys. So first thing we're going to cover is redox reactions, like for the 500th time in your chemistry career. So no, me too. Don't worry. I came to Orgo 2 knowing nothing about acid-base reactions, nothing about oxidation reduction. All I know is Leo goes GERD. That's all I knew. Yep. But now we are about to learn. Okay, so we have. Let's do oxidation. Okay, so these guys are actually like two sides of the same equilibrium. Okay, oxidation. When you do an oxidation reaction, you're making more bonds to oxygen. When we do a reduction, we're reducing the number of bonds to oxygen. That's pretty good. So an example of this reaction is ketone. Draw these arrows, and you're going to tell me which direction is kind of reaction. And I know we haven't covered it, but a pretest. So the top arrow that goes from alcohol to ketone, is that being oxidized or is it being reduced? Oxidized, because we're making more bonds to oxygen. Cool. And so the other direction must be what? And why is it a reduction? Because you're making less bonds. Exactly. Cool. So for this exam, apparently you only need oxidation reduction. So we're just going to cover We're only going to cover oxidation, and then next chapter we'll talk about reduction again. I don't know why he is the way he is. Just the messenger. Yeah, exactly. And okay, technically this isn't the correct definition, like history-wise, but it's good enough for this class. Okay, that's all we need. So for something to become oxidized, there's going to, or the starting materials are always going to be, for this class, an alcohol. So we're going to start first primary alcohols. Secondary alcohols. And last but not least, tertiary alcohol. And I know you can't see it, I just need to get it down really fast. So while you guys draw that, we're going to talk about oxidizing reagents. Does anyone know any oxidizing agents off the top of their head? KMNO4. No. Hold on, I'm gonna. Don't worry. I didn't want to write it. No, stop it. Okay, so as far as oxidizing agents go, we are going to have strong and we're going to have weak. And the reason I copied them over and I don't care enough to memorize all of these is because you don't have to. You could simply think of it as 4 or more oxygens equals strong oxidizing agent. So here we have O4, O7, O4. Oh, but this one's an O3. No, we have so altogether it's O4. So for the rest of the semester, O4 or more strong oxidizing agents. If you are planning to go on and take the MCAT, this is also a good little tidbit to have. Yeah. A lot of stuff, so I'm going to give you a moment. Yes. Yes. Yes, it is. These are basically all strong acids. Okay, so PCC and DMSO4. He doesn't usually test on DMSO4, just know that it's there. Okay, so what's the difference between these two, right? Why do we even care that they are different? I'm going to move this out of the way. So if we have a primary alcohol and it reacts with a weak reagent, let's say PCC, we are only going to remove one of those hydrogens and we're going to make an aldehyde. So in summary, you can say primary OH plus oxidizing agent equals aldehyde. If we use a primary alcohol, but we use a strong, and we can use any of those guys, say KMNO4. We will make the aldehyde, but then we go one step further, and can anyone tell me what it turns into? Carboxylic acid, you were waiting for it. I know this. Okay, So a primary OH plus a strong group equals carboxylic acid. I know I talk really fast, so please tell me if you want me to slow down. Yes. Yeah, so how I think about it is all the oxidizing agents, like you said, are going to give it an oxygen. And the way you get an oxygen is by losing a hydrogen. So since there are two hydrogens to be lost, a weak reagent can only steal one of them. A strong reagent can steal both. So it can replace both of those with an oxygen. The concept you said was right. It was just the wording that. So next we have secondary. So if we have a secondary alcohol and we react it with a weak agent, let's say PCC, what do you think it's going to form? A ketone. Why is that? You're right, but I just need like a why. Anybody? Exactly. So like I said, we're taking away the hydrogen and giving it another bond to oxygen. So we only have one hydrogen to steal, and we make a ketone. You can say, summary, secondary OH plus weak reagent equals. Now, what if we used a strong reagent? What would it turn into? Yay! No, just a ketone. You were looking at me like, was it? Well, you okay? Well, then someone tell me why. Why is it a ketone? Because there's only one hydrogen. It does not matter how strong your reagent is. You only have one hydrogen, so you can only remove one hydrogen. That sounds like such a dumb sentence to say out loud, but you know. Heck yeah, I can. So you only have one hydrogen present. Therefore, you can only steal one hydrogen and replace it with a bond to oxygen. I'll let you marinate on that for a second, and then I'll repeat it. Yes. One second. Let me finish writing this down. Okay. So far, we did primary and secondary, right? Primary alcohols have two hydrogens present. So in the first round, if we have weak, we steal one of the hydrogens. Oh, okay. Okay. So perfect. This is a tertiary alcohol because the OH is attached to a carbon that's attached to 3 carbons. 3 carbons equals tertiary. This OH is attached to a carbon that has 2 carbons and 1 hydrogen. 2 carbons equals secondary. This OH is attached to a carbon that is only attached to 1 carbon, 2 hydrogens. 1 carbon equals primary. Thank you for asking. There you go. I'm sure other people were also. Ah, the win for the whole team. Okay. So let me repeat what I was saying about this one more time. So you can think of oxidation reactions as you're stealing this bond and you're turning it into a bond to oxygen. So here you have 2 hydrogens, but you have a weak reagent. You can only steal one of those bonds. Here you have a strong reagent, so you're going to steal both of these bonds and turn them into bonds to oxygen. This one becomes a double bond, this one becomes an OH. For the secondary, You only have one hydrogen, so you can only make a ketone, no matter what reagent you use. So, what about our tertiary alcohols? There is no reaction. Oh, did you say there is? Obviously. It was me. I was. There it is. That was my trick question for the day. Of course I can. Here, let me make it bigger and then I'll. That's probably. Yeah, exactly. So think of it as. And make sure it's 4 or more, because O3 is something else entirely. And we will talk about that. Well, you guys write this. Yes. Yes. There for a little bit. Why? While I'm here. Okay. Not talked to my supervisor yet, so don't hold me to this. But today, or this week, we missed 6 hours of tutoring because of the holiday, right? And it occurred to me that I can make up these hours. So I'm going to schedule next Tuesday, like this coming Tuesday before your exam, it'll be like 6 hours of tutoring that day. So I'll make 2 hours in the morning, 2 hours in like the afternoonish, and then 2 hours in the evening, trying to accommodate as many as you can. And you can come to me with all your questions for those tutoring hours that don't get answered Monday, because I also have tutoring hours. It's not. I have to talk to my supervisor today, and if my and depending on what she says, that's how it'll go.